Welcome back to my channel Shri Statistics. Today we are going to talk about the Cayley-Hamilton theorem. So the statement of the theorem states that every square matrix satisfies its characteristic equation. So to prove this, let us consider a matrix A is equal to Aij, which is a square matrix of order n. And then A minus lambda I, which is denoted by A naught plus A1 lambda up till A n lambda to the power n equal to 0. This is the characteristic equation of A. So since the elements of A minus lambda I are polynomials of degree at most n in lambda, you will see that the highest degree of lambda here is n. Therefore, the elements of adjoint of A minus lambda I will be a polynomial of degree n minus 1 in lambda. Hence, the adjoint of A minus lambda I can be written as a matrix polynomial of degree n minus 1 in lambda. So let us consider the adjoint over here to be denoted like this: b naught plus b1 lambda up till bn minus 1 lambda to the power n minus 1. So these are all square matrices of the order n. Now we know that the A into adjoint of A over here will be equal to the determinant of A. This is a property. So on applying this property to this value, here what do we get? We substitute the value of adjoint of A over here and the value of the determinant over here as this: A naught plus A1 up till A n lambda to the power n. Now, using the definition of multiplication of two matrix polynomials, we solve this, and for lambda, for this over here, this is the constant term. Then for lambda to the power 1, we get its coefficient as a b1 minus b naught. Then for this again, we get its coefficient and so on. So this is the formula of the coefficient, and this is equal to the right hand side, that is equal to a naught plus a1 lambda plus a2 lambda square and up to a n lambda to the power n into I, which is equal to 0. Now we will be equating these coefficients, that is for say this is equal to this constant. For lambda, this is equal to a b1 minus b naught is equal to a1 and so on. So when we equate these, then what do we get? This is what is obtained. Then pre-multiplying these values by I, then a square, then a to the power n minus 1 and a to the power n respectively, we multiply each value and then we add that. Then what do we get? That 0, first we take a b naught, then a square into b1, because it's being multiplied by a b1 is being multiplied by a minus a b naught over here, then the third term and so on. Then we get that 0 is equal to a naught I plus a1 a plus a2 a square all the way till a n raised to the power a n. This proves that the matrix A is satisfying its characteristic equation, because this was originally the equation for the characteristic equation of A. So hence this proves the theorem.